afternoon, everyone. I am Christal, and I thank you for attending to my presentation. That will be about the effect of chemical heterogeneities, that we call meso-segregations, on fracture toughness of low alloy ferritic steel that is used for large forged components in the nuclear industry. So for the context, in the nuclear industry, some components such as reactor pressure vessel parts or steam generator parts are manufactured from very heavy ingots from 90 to 500 tons. As you can expect, the solidification time of such ingots is very long, thus allowing the diffusion and moving of matter inside the material. Because of this process, the ingot and then the final product contain significant chemical heterogeneities. These heterogeneities are called segregations, and they can be found at different scales. Here you can see a simulation of the carbon content distribution at the end of the solidification inside an ingot. As you can see, the carbon content is higher in the top center of the ingot and lower at the bottom. At this scale, we talk about macro-segregation. At a lower scale, the scale of solidification grain, the mesoscopic scale, we also observe chemical heterogeneities. For those who don't see clearly, the scale is 1 millimeter. And these segregations, they remain in the final product, in the material, despite numerous heat treatments and forging. In the studied material, the ingot has been highly deformed by forging, and thus the meso-segregations are penny-shaped. They are flattened. So, the aim of this study is to evaluate the effect of those chemical heterogeneities, the meso-segregations, on the fracture toughness properties. For that, we used two different materials, one that is highly segregated, that was collected inside the macro segregation. Thus, a relatively high carbon content, on average 0.25%, and it is highly heterogeneous in chemical composition. The other material is the reference material. It was collected in the same component but outside the macro segregation zone. Thus, the lower average carbon content of 0.17%. And this material is much more homogeneous. Here you can see a chemical analysis performed on the highly segregated material through a line perpendicular to the meso-segregations. As you can see, there is fluctuation of chemical alloy composition, main elements, between the meso-segregation that are enriched and the depleted metal. The black line here represents relative hardness variation and is very well correlated with the local chemistry because of the local microstructure that you can observe here. Basically, in the depleted metal, big carbides with small surface, low surface density, and inside the meso-segregation you have smaller carbides and a much higher surface density. We also showed that the average thickness of meso-segregation is around 200 micrometers, and the distance between the segregations are more or less 1.5 millimeters. So, compact tension specimens were used to determine the fracture toughness properties of both materials. Here you can see the experimental data sets, the highly segregated material, represented by the statistical model of the master curve, which means that 90% of the experimental results are located between the two dotted lines. And the T0 reference temperature, which is the temperature where the median KJC is equal to 100 MPa square root of meter. For this material, the reference temperature is -45 degrees. For the reference material, more homogeneous, the reference temperature is much lower, minus 110 degrees. However, this is important, at this point, we cannot say that this difference of mechanical behavior is only due to the heterogeneities, because the average carbon content is very different, and carbon content plays a major role in fracture toughness properties. So to only study the effects of mesosegregation on fracture toughness properties, we did the same experiment but with reduced size samples. Here they are. The mini samples are 4 millimeters. They have a thickness of 4 millimeters instead of 12.5. And here are the results for the reference material. As you can see, there are no difference between the reference temperature measured or calculated with big samples or with small samples. It is totally independent of the sample size. However, for the highly segregated material that is much more heterogeneous, there is a 30-degree difference between both reference temperature. Why? Because when you reduce the thickness of the sample, you increase the sampling effect because of the strong heterogeneity in the material. So that shows that mesosegregations do have an impact on fracture toughness properties. But to understand better this phenomenon, we could use that increasing of sampling effects and using the properties of mini samples that allows the positioning of the entire crack front inside a specific zone, such as a mesosegregation or the depleted metal. And then it's like measuring the properties of both components separately, because the process zone of the sample at fracture is lower than the thickness of the mesosegregations. And thanks to numerical simulation, you could do a model that calculates the stress field inside the highly segregated material, considering the heterogeneity of mechanical behavior of both components. Fractographic analysis were also performed to evaluate the fracture mechanisms of this kind of highly segregated material. Among the 16 samples that were analyzed, only one presents intergranular brittle mechanism. This sample, the fracture surface of this sample is shown here. The red arrows show the propagation of cleavage fracture, and at the center it's the initiation crack site, and you can see intergranular brittle facets. However, for all the other samples, the main fracture mechanism, even at crack initiation site, is transgranular cleavage. Despite what some of the the initiation of fracture could be either on nothing that can be identified, such as here, or sometimes on inclusions, such as titanium nitride. However, we systematically found near crack initiation sites small intergranular brittle facets, although they are never at the origin of the specimen's fracture. To conclude, we saw that local enrichments in chemical composition were very well correlated with local mechanical properties because of the local microstructure that are different. That we saw that mesosegregation do have an impact on fracture toughness properties, but that the predominant fracture mechanism is transgranular cleavage even in highly segregated materials, despite we systematically found intergranular cracks more or less far from the initiation cracks. And for the future work, we saw that we could use the advantage of reduced size sample to characterize both components, so the meso-segregation and the depleted metal, separately in order to implement the results in numerical model. I thank you for your attention.